Good afternoon. How are you? Welcome. Welcome to my YouTube channel. And on this channel, we not only talk about minerals that are not yet mined economically and sustainably, but also talk about those that are being mined efficiently and sustainably. My name is Engineer Mureithi Wanjohi, and today I'm inviting you to join us on the journey that we are going to take in the world beneath our feet, the world and realm of rocks and minerals. With this knowledge, we will be able to understand its significance and diversity. But before we dive in any deeper, I would like to touch on a real and very painful experience by enthusiasts and seasoned collectors. The sting of being scammed. Before we dive in any deeper, I would like to touch on a very painful reality experienced by enthusiasts and seasoned collectors. The reality of counterfeit minerals. I have heard stories about people being scammed, and it's often a very painful reality where your hard-earned money is spent on something that was not what it was said to be. In my opinion, you invest your resources and passion only to find out that you have been misled. But that is about to come to an end. Why? With the knowledge I'm going to share with you today, you will be able to discern and to protect yourself from such deceptions. The knowledge I'm going to share with you today is not only for academic purposes, but also is used in the real world where authenticity matters. So, the first question is, the first question we are going to ask ourselves is, what are minerals? In the naked eye of an experienced person, a mineral is just a shiny rock. In the field of mining and geology, we have a distinct criteria through which a substance, before it qualifies to be called a mineral, must have and is essential for identifying minerals. Think of this as 5 essential checkboxes that a substance must tick so that we can qualify it as a mineral. Number 1, a mineral must be solid. What do I mean by this? A mineral must exist in its solid state under normal conditions. For example, take an ice cube. An ice cube is naturally occurring and it's in its solid form. But I, as a mining engineer, will argue that solid ice cannot exist as a solid under normal temperature, and that disqualifies water as a mineral. Okay, so people talking about mineral water, sorry to say, but it's not mineral. This disqualifies things like atmospheric air, which occurs naturally, and so that is it. A mineral must be solid. Number 2, a mineral must be inorganic. What do I mean by this? A mineral must not come from organic material. It must not be, what do you mean by organic? Organic means it was living at some point of its life. It's like a mineral should come from natural forces of the earth. A mineral should not be living, should not have been living, and should not have come from a living thing. This disqualifies substances like coal, which came from dead plants in the past, or pearls, where they are biogenic. And when you have these two, is it solid or is it inorganic? You are sure to have disqualified most of the materials. Number 3, a mineral must be naturally occurring. What do I mean by naturally occurring? A mineral must come from nature, must come from the earth's geological processes. This, as we had earlier discussed, disqualifying atmospheric air, which occurs also naturally, but it is not in its solid state. But now, if it is in its solid state, but did not occur naturally, or it was constructed in the lab or constructed in the construction site, that disqualifies it as a mineral. So we have 3 boxes that we have already checked. It must be solid, must be naturally occurring, and must be inorganic. Number 4, a mineral must have a specific chemical structure. Each mineral has a specific chemical structure or a range of formula dictating its atomic makeup. Okay, for example, we have quartz. Quartz has a specific chemical structure, given that it may appear in different colors. You can have clear quartz, you can have white, you can have pink, you can have smoky quartz, but its chemical composition, which is silicon oxide, is basically, it's at the very bottom. It's the fundamental of quartz. Think of another mineral like halite, which is commonly known as rock salt, which has its chemical composition as sodium chloride. In whatever color it appears in, or in whatever form, sodium chloride is its baseline, its chemical structure. Number 5, given that a mineral is solid, a mineral must have a unique crystal structure. This is the most defining characteristic, okay? Minerals possess an ordered internal atomic arrangement, forming a repeating pattern known as a crystal lattice. The internal crystal arrangement is unique in every mineral, okay? You can have a mineral like quartz, which is crystalline, and a good example is halite, because we all know table salt, which appears in cubicles. This unique crystal structure is exhibited externally through its shape. So we can, with these 5 characteristics, these 5 essential boxes ticked, you can be sure that what you have in your hand is a mineral. It is solid, number 1. It is inorganic, number 2. Number 3, it is naturally occurring, okay? Number 4, it has a unique crystal structure, and number 5, it has a specific chemical composition. The first question was, what is a mineral? And we identified them with the 5 check boxes. The next question is, how do I identify a mineral? Geologists have sophisticated and advanced technologies which can help to identify minerals. But these technologies and techniques are not readily available to us on the ground when we find certain minerals. And sometimes we want to identify them before we even undergo the cost of going to the lapidist and asking them what is this, the consultancy fee of finding a mining engineer and asking them what mineral is this. So there are simple ways to identify a mineral, how to identify a mineral, and the first way is by identifying its physical characteristics. Okay, so physical characteristics are clues left behind by the mineral internal structure to help us identify and distinguish from one mineral from the other, remembering that each mineral has a specific crystalline structure and a specific chemical composition. So these are clues of the interior of the mineral, helping us to decipher one mineral from the other. So the first physical characteristic you notice is the color. And many can attest have fallen to this trap. Color is the primary, the first thing you see. But, disclaimer here, color alone cannot be used to identify a mineral. Why, you may ask? Minerals, some minerals have a range of colors. Some minerals might have a kind of almost specific color, kind of like magnetite, which is almost always green, but we have quartz, which is white, clear, rosy pink, smoky. So color alone cannot be used to identify a mineral, but with conjunction or with when you combine the color characteristic with other characteristics that I'm gonna share, it can help you narrow down to what the mineral might be. So the first one that we have discussed is color. Number 2 is hardness. This is the property of a mineral that measures how the mineral is resistant to scratching. It's quantitatively measured by Mohs circle and has an ordinary scale of 1 to 10, which 10 is the hardest known mineral, diamond, and 1 is the softest, and we have a mineral like talc. So when we are on site, when we are at the ground, we can use our nail to determine its hardness. Our nail has a hardness of around 2.5 on Mohs scale. A copper penny has 3.5, and a steel knife, depending on the quality, has around 5.5, and we can have glass, which is 6.5, 5.5 to 6.5. What do I mean by this? If you scratch a mineral and you find that your fingernail can scratch that mineral and make a dent on it, it means if the finger has a hardness of 2.5, then the mineral is less than 2.5. If it is scratched by a copper coin, which is 3.5, then the hardness of that mineral is less than 3.5. The same goes to a steel knife. A steel knife which has 5.5, around 5.5, depending on the quality of the steel nail. If it scratches it, it is below 5.5, but if it does not make a dent on it, it is above 5.5. And mostly we have glass. Glass has a hardness of 5.5 to 6.5. If the mineral can make a dent on the glass, it means it is harder than glass. So it is higher than 5.5. But if it slides on glass, it means the mineral has has a hardness of less than 5.5. Hardness is one of the most reliable properties that we can use in conjunction with the other properties. It can help us narrow down on the mineral which we are in question of. So we have talked about the color, and then we have talked about hardness. The third one we are going to talk about luster. So what is luster, you might ask? Luster refers to the way light reflects off the surface of a material. It describes how shiny or dull a material appears. Luster is widely divided into two. It is divided into metallic and non-metallic. So luster shows how light behaves on the mineral itself. Does it reflect it? Does it absorb it? Okay, so if it is metallic, then the luster resembles the sheen of a polished metal, appearing reflective, and most of the time it's opaque. And if it is non-metallic, now that is where we have a wide range, where you might find a mineral is glass-like, like quartz. You might find a mineral is pearl-like, like talc. You might find a mineral is dull-like. For people living in the western area of Kisii, where kaolin comes from, then you might know how kaolin looks like, and mostly kaolin is dull. And there is another mineral which is greasy, like it's as if oil has been applied on it, called serpentine. Okay, so we have talked about color. So if you had your chart, you have seen that, okay, this is a mineral, this is solid, it is natural, it is inorganic, it has a unique chemical composition, it has a unique chemical structure. You go now to the next step. You look at the color. What is the color? And then after the color, since it's not much reliable, how hard is it scratching the glass? Is it how does it behave with light? How does it does it look metallic? Does it look non-metallic? Those are the questions that you have to ask yourself before even beginning to purchase a mineral. So we have talked about color, we have talked about hardness, we have talked about luster. Now number 4, we talk about the streak. Streak is the color of the mineral in its powder form. Surprisingly, you will find that a mineral has a different color from its mineral. Okay, like the mineral itself has a different color than after it is in powder form. How do you realize its powder form? You take the mineral and take a ceramic, the back of a tile, the tiles we use at our house. Take a piece of it and scratch at the back of it. You might find that it is very different. I'll give you an example of gold and pyrite. Pyrite is commonly known as the fool's gold. Both of them have around the same color. They have the reason why pyrite is known as fool's gold is because it looks like gold. So to differentiate the two, you use streak. when you uh, use the tile and rub the piece of material that you think is gold on that on that ceramic plate. For gold, it has a yellow streak. For pyrite, it has a dark green streak. You see, that is another way you can differentiate the two. Okay, another one is like this one we have for iron. It's called hermetites. Now, hermetites, there there are two types. There is one which is silvery gray, and there is reddish brown. But here's the catch: when you put it in their powder form, or when you rub it against the behind of a tile, you find that both of them have a reddish brown streak. You see, that is how you differentiate uh, whether it's this mineral or another one. So we have talked about hardness, we have talked about color, we have talked about luster. Now I want us to talk about cleavage and fracture. Okay, what is cleavage and fracture? Cle- uh, this property describes how a mineral breaks. It reveals the internal atomic arrangement of the mineral, and it shows it looks as if it comes from the inside. So what is cleavage? Cleavage occurs when a mineral breaks along the planes of weakness within its crystal structure, producing a smooth parallel flat surface. Okay, we find this in like halides, which produce cubes. We find it in calcite, where when you break it, it forms rhombohedrals, and there is also the micas like biotite. When you break it, they become like thin flexible sheets. It's my Minerals are another world which will just be fascinated about. There was a time I found a mica biotite, and I was like, wow, does this even exist under the ground? Anyhow, we go back. Okay, now for fracture occurs when a mineral breaks irregularly, and this happens when the atomic bonds have equal atomic strength in all direction. Okay, so when you find that when you break it, they just scatter into pieces. Rather, in comparison to the hematite, when you break it, it scatters into cubicles. Okay, so we have had those four or five. Four or five. We have color, we have hardness, we have luster, we have cleavage and fracture. Now, those being our basic, there are also other ways to identify your mineral. Sometimes you can taste it. It is not advisable to taste things that you don't know where they come from, but there there are minerals which have a certain taste. We have like halite, the rock salt. When you lick it, it's salty, obviously. But it is not as obvious as it seems right now. But when you are at the ground, you when you lick it, you'll know it is salty, so it has some properties of halite. Do you understand what I'm saying? And then there are properties like smell. Uh, when you find a mineral like sulfur, when you crush it, it smells like rotten eggs. And if you can remember your chemistry well from high school, one test to know that it produces sulfur something was you swaft the air to your nose and it could smell like rotten eggs. The same to the mines. When you have that stone and you crush it and then smell it, it will smell like rotten eggs. There are some minerals like magnetite which have magnetic properties, so they attract other magnets. That is how you can decipher that you have a magnetite rock. There are some minerals which have refractive double refractive double refractive properties. Like a clear calcite, when you look at it, you'll see as if you're seeing items in double, in twice, up and down. Those with eye problems can say something about it, but I rest my case. And then there is another property like effervescence. Effervescence, where when you find a mineral like calcium carbonate, when you pour dilute hydrochloric acid, it starts to effervesce, it starts to remove bubbles. It's the reaction between an acid and a base. That is like a carbonate. When you pour dilute hydrochloric acid, you find that it effervesces, and that is how you can test for limestone, which is calcium carbonate, or dolomitic limestone. So now that we have our physical properties, we have talked about what is a mineral, number one, and we said the 5 boxes we check. And number two, we have talked about how we identify a mineral. That is the physical properties we look at, which shows the internal structures, the internal properties of the mineral and its chemical and unique crystal structure. Now, the other question we are logically allowed to ask ourselves is, why do certain minerals have different chemical properties? Okay, not okay. So, chemical properties. I want us to dive a little bit into 2 minerals that we know of. We have diamond and graphite. Okay, so diamond is formed from carbon, and also graphite is formed from carbon, but yet they have different properties. You find that diamond is the hardest rock with a Mohs-Sahko scale, on the Mohs-Sahko scale, with scale of 10, while graphite, on the other hand, is soft and slippery and is used in pencils. Graphite is dull, while diamond is used in jewelry and it's shiny, it's glassy. You find that diamond is used in drill bits, and the other one is used in pencils. Why is it so? Yet both of them are formed from the same, have the same chemical background. To differentiate between diamond and graphite, it is only fair enough to double down on their atomic structure, where diamond has a 3-dimension tetrahedral lattice, making it incredibly hard, while on the other hand, graphite atoms are arranged in hexagonal sheets that are bonded together by weak van der Waals forces, which make it easy for them to slide over each other, giving them that soft characteristic. Okay, this striking contrast perfectly illustrates mineral properties directly manifested in the atomic structure. That is why you find that A mineral might be composed of the same chemical properties or have the same chemical background but have different uh, characteristics. Okay, now with that we have discussed what is a mineral, and we've said about the 5 check boxes. We've said about them being natural, them being solid, then having a unique chemical structure, them having a unique crystal structure, and them being natural, that is, not have been constructed from anywhere or from any lab. Now I want us to embark on rocks. It is a slightly different, they are slightly different from minerals, but in the same geological family. Now, on a slight note, minerals are the building blocks of rocks. But what exactly is a rock? A rock is a naturally occurring aggregate, one which is formed by one or more minerals that are formed together. Okay? Unlike minerals which have a specific chemical structure or a specific or a unique crystal structure, minerals are a mixture. Pardon me. Rocks are a mixture of all of this. And rocks are classified into 3 major categories. One of them being igneous rocks, metamorphic rocks, and sedimentary rocks. Magma is when molten rock solidifies beneath the earth, while lava is molten rock that cools and solidifies above the earth. These two form different igneous rocks, and this brings us to the 2 categories of igneous rocks. We have intrusive igneous rocks and extrusive igneous rocks. Okay, so intrusive igneous rocks is when hot magma cools and solidifies beneath the earth slowly to form rocks, while extrusive rocks is when lava solidifies and cools above the earth to form rocks. Okay, since the two are formed in different places, they have different characteristics. For intrusive rocks, they form underneath the earth where it's hot and the process is slow. So crystals are given an opportunity to grow and to form and to solidify to get to their peak. Like, they are given time for the crystals to form. While in extrusive igneous rocks, the cooling is more rapid, more quickly, so they are not given time to form crystals, or if they are given time to form crystals, they form tiny crystals which are not visible to the eye, the naked human eye. So I have an example of an extrusive rock. Here it is. Now, this extrusive rock, let me surprise you. I brought it home after we went on a trip when I was in class 7, I think. I brought it back from home from a trip. We were in Hell's Gate here in Nairobi, and I never thought I would become a mining engineer. But I had a passion for rocks since I was a little young man. So this is an extrusive rock. As you can see, it is all black, and the reason why we have a difference between extrusive and intrusive rocks, the intrusive rocks have big particles. An example of an extrusive rock is granite. You can see the black particles of biotite. You can see the pink, purplish color, that is feldspar, potassium feldspar, and then you can see the white crystals, that is quartz. Because they were given a chance for them to form, they are visible in the naked eye. While in the other hand, the extrusive rock form quickly, and sometimes you might find that they form so quickly that air bubbles are stuck inside the rock, giving them a rough texture. And these holes are called vicious or verticals. Just call them holes. You can actually see them right here. These are air spaces that were left behind by when this rock was cooling. Okay, it cooled so fast that you can't see them you can't see the particles. It's all black, and without a microscope you can't really see what particles are inside here. But this is an example of an extrusive rock. So for just a recap, we have said igneous rocks are divided into two categories. We have intrusive igneous rocks and extrusive igneous rocks. Intrusive igneous rocks are formed when hot magma cools and solidifies beneath the earth slowly to form rocks, while extrusive is lava that cools and solidifies above the earth. For intrusive rock, they are given the other name for intrusive rock is plutonic rocks, and for the other name for extrusive rock is volcanic rocks. Now that we are done with the igneous rocks, we go to metamorphic rocks. Okay, and before we get into metamorphic rocks, this is a glassy obsidian rock from Hell's Gate, and big shout out to my mom who uses it as decoration in the house. Who knew that it would one day be useful? So everything happens for a reason. I trust that. So metamorphic rocks. Okay, metamorphic rocks come about when the rock and a previously existing rock is exposed to heat and or pressure so much that it doesn't melt the rock itself, but it changes its properties. So a metamorphic rock occurs when a rock is exposed to heat and or pressure. You realize that I'm saying heat and or pressure because the two can work in conjunction, or they can work in a solo. In the solo version, it can mostly be heat, and it can sometimes be pressure. So a metamorphic rock comes about when a rock is exposed to too much heat or pressure, so much that it does not melt the rock, but it changes the external and internal chemical structure of the rock. Now that we have said end or pressure, this means that there are two categories of metamorphic rocks. The first category is a contact metamorphic rock, while the other category is a regional metamorphic rock. Okay, the contact metamorphic rock is mainly due to heat, where imagine hot magma being poured on a rock so much that it does not melt the rock, but it changes the internal chemical structure and the external appearance. So a contact metamorphic rock occurs when hot magma comes into contact with the rock. The name actually says it's contact, so it's when hot magma comes into contact with a rock, not enough to melt the rock, but the heat is enough to change the internal structure and chemical structure of the rock, giving it an external new look. While regional metamorphism is when the rock is exposed to too much pressure. This pressure is mostly caused by the movement of tectonic plates, such that the rock metamorphosizes to change its internal structure and to change the way it appears. Okay, so we have contact metamorphism and regional metamorphism. Metamorphism is just a transition of an existing rock. It might be an igneous rock, it might be a metamorphic rock, or a sedimentary rock, which is exposed to heat and or pressure. That is, it can be metamorphosized through contact or regional metamorphism to change its internal structure and external appearance. Now that we are done with igneous rocks, where we have subdivided it into intrusive igneous rocks and extrusive igneous rocks, we have talked about metamorphic rocks, where we have subdivided the two into contact metamorphism and regional metamorphism. Now we go in deeper to sedimentary rocks. Okay, what are sedimentary rocks? Sedimentary rocks form as a result of compaction and cementation of rock sediments. Okay, rock sediments can come from the weathering of other rocks and then transported to a certain area by wind or water. That is, rivers carry sediments of rocks from one point to another. Wind can carry rocks from one point to another. So sedimentary rocks are classified into two. There is kalastic rock, kalastic sedimentary rock, and organic sedimentary rock. Kalastic sedimentary rock are just rocks which have been compacted and cemented due to pressure. Organic sedimentary rocks are rocks that can be made through two processes. One, there is when water leaves behind the sediments after it evaporates, and now it becomes a rock. The second one is when dead plants compact together in cement to form a rock. For the first one, we can have rocks like salt rock or dolostone for when water evaporates and leaves behind the rock. While for the other one, we have, for the one plants die and leaves and the dead material compacts and cements, we have coal and coquilla. Okay, so for sedimentary rocks, we have kalastic rock and organic sedimentary rocks. So to sum up everything that we have learned today, we have talked about what is a mineral, how to identify a mineral. What is a mineral? We use the 5 check boxes that we mentioned. Must be solid, must be naturally occurring, must be inorganic, must have a specific crystal structure, and must have a unique chemical structure. We also talked about how do we identify a mineral. One, we can use the color, and then we can use hardness, which I remember giving you tips on what Niels hardness was. And then we have a cleavage and fracture, and then we have others which we talked about, like smell. We talked about the refractive index, and then we talked about the properties of some minerals which have magnetic properties, like magnetite. To use a magnet. So we have talked about what is a mineral, how do we identify a mineral, what can be the reason of the different minerals that have the same chemical background. We talked about diamond and graphite, how diamond has a tetrahedral type of chemical structure, and how graphite has a hexagonal plate kind of structure. And then we have talked about rocks. What are rocks? They are aggregates, and their building blocks are minerals. And then we have talked about what types of rocks. We have talked about igneous rocks, we have talked about metamorphic rocks, we have talked about sedimentary rocks. Now we come down to this knowledge can help, is crucial for our day-to-day living. For the ones who are still in school studying geology or mining, this information today gives us a foundation to lay, so that when you extend, you can be able to categorize rocks and minerals into these different categories. For the enthusiast and active and seasoned collectors, now I have empowered you today with the knowledge of how to identify a mineral. There is no more being scammed anymore if you have watched this channel. So for those watching this channel, please share this content, because if you have felt the pain of being scammed, I don't know why you should let another friend go through the same pain so that he can find this content on his own. Just share it and help a brother have a smile. Okay, so I'll leave behind some links in my description. One, I'll leave behind a document that you can you can use to classify minerals. Number two, I'll share my website link, where you can share your comments on new minerals, and I can help you decipher what kind of mineral it is. And that is the end of our content today. So have an awesome time, and in Japanese we say Janne sayonara, bye and goodbye. Have an awesome time, and see you in my next video. Thank you.